Hello, welcome to biology. We're going to be talking about chapter 2, the chemical foundation of life, and that is in the OpenStax Biology 2E textbook. In this chapter, there are 3 sections. So section 2.1 goes over atoms, isotopes, ions, and molecules. So we're going to talk about matter and elements. We'll also talk about protons, neutrons, electrons. We're going to talk about how those electrons impact matter. And we are going to look at how elements combine to form molecules, then they form cells, and so on. So atoms are the building blocks of all molecules. Life is composed of matter. Matter has mass and it occupies space or takes up space. And so elements are atoms. And elements, they each have their own unique properties. So they each have their own chemical properties, their own physical properties. So take an element of helium. Its chemical properties is that it does not react. It is a noble gas, if you know anything about chemistry. It is happy the way it is, and its physical properties is very light and it floats. And so each element or each atom behaves differently. Elements in the living world. Elements cannot be broken down into smaller substances while still behaving in their specific manner. So we can't break down helium and still have it be helium. Each element is designated by a chemical symbol. 1 letter would be capitalized. 2 letters would have a capital and a lowercase. The 4 most common elements for all living organisms are carbon, oxygen, hydrogen, and nitrogen. So if there is a living organism, it's going to have those 4 elements in it. And that's a nice way to look and see if you have any living organisms, say on like a planet. Here is the percentages of those 4 elements. So oxygen in life, living life forms, it's about 65%. Notice the difference. In the atmosphere, it's about 21%. In Earth's crust is about 46%. So living things have different ratios of these elements than does the atmosphere and the Earth's crust. Very different. So atom, again, is the smallest unit of matter, and it retains all the chemical properties of an element. Atoms contain 2 regions. There's a center region called the nucleus and an outer region which holds electrons. In the nucleus, the center region, it's a little positive. It contains protons and neutrons. The outermost region is a little more negative, and that contains electrons. And so these 3 things together, protons, neutrons, electrons, are all called subatomic particles. So you may have heard that term before. It just refers to those 3 things that make up an atom. Here's what it looks like. Here's the nucleus portion, so that center portion with those positive protons and neutral neutrons. And then the outer region out beyond the nucleus is where we can find electrons. Notice how small they are, and they are negative, so that outer region is going to be a little more negative. Okay. So here's a quick table that summarizes that information. Proton has a +1 charge, or it's a positive. It has a mass of 1. AMU means atomic mass units, and that's its location. Neutron, same location, same mass, no charge. Electron has a negative charge, no mass, because it's so small, it's negligible. It does have a very small amount of mass, but we'll say it's negligible for us. And it's in that outer orbital. Okay, so you should be able to fill this information in. A should be a neutron. Let's go over to B. B should be electrons. Over to C. C is pointing to the nucleus region. And D is referring to those protons. So if you need to pause it and fill it in, try it yourself. That would be good practice because you'll likely see something like this on an upcoming quiz or test. Okay, so what's the difference between atomic number and atomic mass? You've probably heard these before and you probably got them mixed up, and that's totally fine because they sound so similar. So atoms of each element, they have a standard number of protons and a standard number of electrons. So that atomic number actually refers to that standard number of protons. So for example, carbon's atomic number is 6. So anywhere you see it on a periodic table, its atomic number will be 6. That means it's going to have a standard number of 6 protons, okay? Atomic mass is going to talk about the mass of the atom. Remember, if we go back to this table, what has mass? Protons, yes, but also neutrons. So we can talk about the atomic number of carbon being 1, and if it has, being 6, and if it has 6 protons, then that makes up 6 of its mass. Well, carbon also has neutrons, and so those neutrons account for mass as well, and it also has 6 neutrons. So added together, 6 and 6 is 12. So it has a mass number of 12, and that's for carbon. So again, just to summarize, atomic mass is equal to protons and neutrons. So protons are the amount of positive, or the atomic number is the amount of positive particles, or the protons. And atomic mass is the positive protons and the neutrons. So the total mass, what makes up that atom. So remember, atoms are made up of not just protons, but protons, neutrons, and electrons. So we have to account for all of those. Now we can have different things called isotopes, and isotopes will differ in the number of neutrons in the nucleus. So for carbon, we can add another neutron and it becomes a carbon-13, so mass of 13. We can add 2 neutrons and it becomes carbon-14, or a mass of 14. So isotopes, again, we don't change the number of protons, we're just changing the mass, making it heavier or lighter by changing that number of neutrons. So here again, just to review, atomic number is going to be up here in the corner, typically the smaller number. For carbon, it's 6, so that's 6 protons. And its mass number is 12. So we know it has 6 protons. We can just subtract 12 minus 6, and we know that there's 6 neutrons. Pretty simple, right? Okay, so answer this question. If xenon has an atomic number of 54 and a mass of 106, how many neutrons does it have? So what are we going to do? 106 minus 54, and it's going to leave us with 52. Yeah, so 52 neutrons and 54 protons make up the mass of xenon, which is 106. All right, a little bit more about isotopes. So isotopes, again, are different forms of an element, meaning that there's different numbers of neutrons. We can change the number of protons without changing the element, but we can change the number of neutrons while still keeping the same element. So all of these are forms of hydrogen, and they get really special names. So hydrogen 1 has no neutrons, it's just a proton in the center. Hydrogen 2 has a mass of 2, and so it has a proton and a neutron. And hydrogen 3 has that 1 proton still, because it's still hydrogen. And we added another neutron, so we made it heavier. Okay. There is a simulation. This one's from the textbook. You can follow the link in there, and that it kind of helps explain what an isotope and atomic mass account for. All right, the periodic table. You've seen this many times, I know. The periodic table is arranged by atomic number, and the atomic mass is located at the bottom. Notice it is a decimal. That means it's just the average atomic mass that we could find that element in. Round it to the nearest whole number for our purposes. Electrons, so let's talk about those. We just talked about protons and neutrons in the nucleus. Let's talk about electrons out in the orbital. So electrons inhabit very distinct orbitals if we go by the Bohr model, and they look like this. They have different sub-levels. Notice they are numbered there. And so that's just saying where we're likely to find electrons. Electrons will normally inhabit the lowest orbital or the closest orbital to the center of the atom, and will fill them going outward. Okay, so electrons fill orbitals closest to the nucleus first, then those further away in order. So as these orbitals fill up, we'll go to the next one. As that orbital fills up, we'll go to the next one, and so on and so forth. And again, this is a Bohr model. It is highly simplified for our sake. So let's take a look at some atoms here. These are some atoms that are pulled from the periodic table from different groups. So group 1 or column 1 on the periodic table, this is group 14 or column 14, group 17, group 18. Group 18 is the very last column. So each of the red circles are showing you a very important part of every atom. These are the ones that we are concerned with. So when elements bond to one another, they're going to bond by either losing or sharing their electrons. And the ones that they lose or share are in, you guessed it, this outer orbital. They're not going to lose or share the ones that they're holding kind of tightly close to themselves. They're going to lose or share ones that are, a little further away that they don't like as much. So that's why these are highlighted, and that's why they're important. So they're called the valence shell, and they're just the electrons that are kind of left over in that outer shell or outer orbital. Really important, group 18, the very last column on the periodic table, holds helium, neon, argon, and so forth. Their outer shell is full, and so they aren't going to gain or lose any electrons. They are actually happy as is. Notice, like chlorine here, we've got one missing here, so it's not happy. All of the elements on the periodic table want to be like a noble gas or an element in group 18, for instance. And so they're going to try to get to that point by gaining or losing or sharing electrons to look like a noble gas. Everybody wants to be a noble gas. When the first two outer shells are filled, that's called an octet rule. And so we reach 8. So notice there's 2, 4, 6, 8 here on that outer orbital. So every element wants to try to get to that 8, except for the first two elements, hydrogen and helium, because they don't have enough electrons to even get to 8. And so they're going to go to just 2. So just hitting this again, Bohr models are incomplete. They're highly simplified. Electrons don't actually orbit that way, but they do inhabit specific orbits, and I'll show you that. If you want to go into quantum mechanics, that helps predict where electrons might be at any given time. They are moving very fast, and so it's hard to pinpoint where they might be. And so that's where quantum mechanics comes in. So this is actually a representation of how electrons orbit around an atom. So notice the first 2 orbitals are circular, but beyond that, they start to get this like dumbbell shaped pattern. It's really odd, right? So those are specified as SP, D, and F. We're not going to get into all of the specifics with those, but that's just something I wanted to show you. Okay, so electrons, I told you they're important for chemical reactions. Electrons are what comes into play when we combine chemicals. And so they're going to get rearranged, and we're going to redistribute those electrons, and that's what helps create new molecules. And so the chemical bond that forms between elements is actually the attractive force between electrons, or gaining or losing, so on and so forth. So just to recap here, what you probably already know, what goes into a reaction is called a reactant, and what comes out of a reaction is called the product. This reaction is showing you hydrogen peroxide breaking down into water and oxygen. So we get some bubbles of oxygen out of that. This reaction is called an irreversible reaction. It only proceeds in one direction until all the reactants are used up. So as we use up all the hydrogen peroxide, we'll just end up with only water and oxygen. A reversible reaction has an arrow going both directions, and this is going to be a reaction that reaches equilibrium. So we're not going to use up all of the reactants or all of the products. They're going to reach a state that the living thing is happy with, or equilibrium. Covalent bonds. So during a chemical reaction, we're going to change where electrons are, correct? Chemical covalent bonds is how we share electrons. And so covalent bonds can be found in water molecules, for instance. A hydrogen atom and an oxygen atom are going to share a pair of electrons to reach that octet rule. Remember that octet rule is 8 electrons in that shell. That's a full shell. For hydrogen, it's just 2 because it doesn't really hold that many, so 2. But hydrogen has 2 that it has there. Oxygen has its 8, and then this other hydrogen is sharing 1, and that also has 2. So that's a covalent bond. Covalent bonds are pretty strong. You can also have a double covalent bond. You can also have a triple covalent bond, and that's just talking about the number of pairs that are shared between elements. So, for instance, these oxygen molecules have a double bond because they're sharing 2 pairs between them. Ionic bonds are a little different. They don't share. They kind of just rip the electron from the other one. So sodium, it has 1 electron. It's a lot easier to give up 1 than to try to gain 7 to reach that 8. And so if it gives up 1, chlorine will happily take it because it needs 1 to get to 8. And so that would be an ionic bond. Sodium is giving up an electron. Chlorine is gaining an electron. And then this attraction that's created between the positive and negative sodium and chlorine is where that bond comes from. So this is a very strong bond. It's usually between a metal and a non-metal. But yeah, that's ionic bonding. Okay. Another type of bond is a polar covalent bond, and that's an unequal sharing of electrons. So yes, the electrons are shared like in water, but oxygen's a little bit bigger, a little bit more of a bully, and so it's going to hold those electrons just a little bit closer to itself than hydrogen. So it's sharing, but it's not being very nice about the sharing. And so it gets a slight negative over here because the electrons are closer this way, and a slight positive because the electrons are a little further away. And so this is called a polar covalent bond. A nonpolar bond is where electrons are shared equally. And so they're going to be like halfway between each and every one of those. So notice we don't have any partial charges here. And then here's another type of nonpolar. No unequal sharing there. Okay, another type of interaction is called a hydrogen bond. You also have a van der Waals interaction. Both of these are between molecules. So they don't actually happen in a molecule, but they do happen between adjacent molecules. And these are going to be super important, like in, for example, DNA. DNA, in between the 2 strands, there are hydrogen bonds that hold that DNA ladder together. They are super weak bonds, but without them, life wouldn't proceed as it does. So they're easy to get ripped apart. They're easy to get put back together. And that nature of them helps, living things prosper. Okay. So that's 2.1. Make sure you know what a matter and element is. You can define both of those. Make sure you know what a proton, neutron, electron are. Make sure you can compare covalent and ionic bonds. And hopefully you can talk about how we combine elements, what actually is happening. So remember those electrons. So if you don't know those things, go back, rewatch. But we're going to continue on here. Next section is 2, water. We're going to talk about the properties of water, why it's a solvent, why it's super important being in a solvent, as a solvent. We'll talk about cohesion and adhesion and acids and bases and buffers. So water makes up 60-70% of the human body. It's the most critical molecule for life on Earth. Earth has all 3 states of water present, and so that's probably why we have so much life and why Earth is such a great planet. It is a polar molecule, which means it can dissolve things. We'll talk about that in a second. And it can also form hydrogen bonds. So we just talked about hydrogen bonds. They are weak interactions between molecules. So in this case, we're talking about between water molecules. So again, on Earth, we have 3 states of water: liquid, gas, and solid. I'm not going to get into those. Hope you know that. Water, again, has a polar covalent bond within it. So between the oxygen and hydrogen, we have polar covalent bonds. The oxygen holds those electrons a little bit closer, so it's a little negative on that side. Hydrogen, since the electrons are further away, it's a little bit more positive on the hydrogen side. That partial negative, creates attraction between the other water molecules, partial positive, partial negatives. And so that keeps water together. So if you ever notice like dew that bubbles up, it's going to make a nice like 3D effect, right? And that's because all of those water molecules are sticking together. And so hydrogen bonding, when we freeze water, it makes ice less dense than liquid water, and that's why it floats. It creates a nice lattice structure, and the molecules are so far apart that it's less dense. It's not as heavy, and so it floats to the surface. Other important properties: the heat capacity of water. It takes a lot of heat to raise the temperature of water. And so it can absorb a lot of heat. So think about like in the summertime, when you're at the beach, and it's like May or June, and it's been hot for, a few weeks. The water's still going to be pretty cold, right? The ocean water is still going to be pretty cold. And that's because water takes a long time to heat up versus, say, land, like concrete. Okay. It also takes a long time for it to cool down. So in the wintertime, coastal cities aren't going to get that cold as an inland city might, and that's because they're controlled by the heat of the water that they're nearby. It also takes a lot of heat to change water from liquid to gas, so evaporation. It's going to take a long time for that to happen as well. So I mentioned earlier that water is a very particular solvent, and that's because it's polar. And because it has those slight positives, slight negatives, it can dissolve many, 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 many things. And so we call it a universal solvent. So water is typically going to have minerals dissolved in it, such as sodium and chlorine, like the ocean. And this is how it looks if we were to drop some table salt into some water. This is exactly what happens. So that sodium chloride bond gets broken apart. The partial negative oxygens are attracted to the partial positive, or not partial, fully positive sodium. And the opposite happens over here, that chlorine is negative and it attracts the partial positives on those hydrogens. And so that actually rips that sodium chlorine apart and dissolves it. Yeah, just like that. So water is a universal solvent. Other important properties: cohesion. Water can stick together, can stick to, and that's due to hydrogen bonding. Cohesion also allows for surface tension. So the capacity of a substance to withstand being ruptured. So like this needle floating on top of water here, that's due to cohesion. Adhesion is the attraction of water molecules. So capillary action or capillary attraction happens in plants. That's how water moves from the roots to the shoots in plants. And that's from that pull on water molecules. So as one is pulled, it pulls the next one, and that one pulls the next one, and that one pulls the next one. It's kind of like a train, and it's just pulling right along, and that's adhesion. In the real world, you've probably seen one of these before. These are water striders, and they stay afloat on top of water because of water's cohesive and adhesive properties, because water wants to keep sticking to itself. And so it's not going to allow that bug's leg to protrude into the surface. Okay, so answer this question. Which of the following statements is not true? It would be D. Water makes up 60 to 70% of Earth's atmosphere. This should say the human body. Okay. pH buffers acids, bases. So pH indicates acidity or alkalinity, so acid or base, and a small amount of water molecules. As they ionize or dissociate, we will get hydrogen ions and hydroxide ions. And so hydroxide is going to indicate an acidic solution if we have more of those. If we have more hydroxide ions, we'll have a more basic solution. But if they are in balance, we'll have a completely neutral solution. And so a neutral solution is indicated with a pH of 7. And that has to do with a logarithmic formula, which we won't get into. But a good example of that would be like distilled water. If we have more hydrogen ions in the solution, it'll be acidic. So that's below a 7. So you take a look at all the examples here. And then a basic solution would be more hydroxide OH molecules, and that's above a 7. The human body is about a 7.2, 7.4. We're a little bit more than neutral. And you can see seawater is an 8, black coffee is a 5. So you can throw your pH off by drinking coffee or orange juice. You'll make it more acidic. And so your body has to react to that by using a buffer system. So buffers play a key role in maintaining internal pH. And so this diagram is just showing you the body's buffering of blood pH levels. So if it gets too low or too high, it's going to drive the reaction in a different direction. So we talked about this earlier with a double arrow. That would be a reversible reaction. So it can go to the right or it can go to the left, just based on what the living body needs. Okay, answer this question. Which of the following statements is true? It should be C. Acids, but not bases, can change the pH of a solution. So both can, right? Acids and bases can. Okay, and that's section 2, water. So you should be able to talk about the properties of water that are critical, why it's a solvent, or why we'd call it an excellent solvent. Talk about what cohesion and adhesion are, and what an acid and base is, and why buffering is important in a living body. All right, the last section, section 3, which talks about carbon. We're going to look at why carbon's important for life and describe what functional groups are and why they're important in biological molecules, which leads us into our next section. So carbon is important. If you ever take organic chemistry, you're talking about carbon and you're talking about living things. So carbon is a key component of all macromolecules, those major 4, which we'll talk about next week. Proteins, carbohydrates, lipids, and nucleic acids. They all have carbon in them. Carbon is awesome because it can form covalent bonds with 4 different atoms. So it can make some really large and complex molecules. It allows to be the backbone. It has 4 electrons in the outer shell, meaning it can form 4 bonds because it needs the 4 fill 4 more areas to reach that 8. And it allows it to achieve that octet rule when we do fill those. Okay, so each carbon atom, I just said it, it can form bonds with as many as D4 atoms. All right, hydrocarbons. You may hear this term a lot. Hydrocarbon refers to a molecule with carbon and hydrogen in it. And so this molecule is going to have a lot of bonds. Bonds store energy. When we break those bonds, we release energy, like the fire in that picture there. So this bond, these 4 bonds here, have a lot of energy stored in them. So if we burn it, methane, if you know what it is, it's a gas. And so it's a fuel source. And so it releases a lot of energy when we put some fire to it. The energy release powers our homes, cars. It also is in a lot of the food that you eat, hydrocarbons are. And so they provide your body with a lot of energy. Hydrocarbons are arranged differently. We're not going to get super deep into this, but I just want you to look at the complexity that you see here. So this methane is in like a pyramid format. This ethane, so 2 carbons, 6 hydrogens there, very complex structure. And then ethene has a double bond. So many different ways that we can arrange the hydrocarbons. And they're only showing you up to 2 here. They can get very, very long and complex, and I'll show you in a little bit. So here's some rings, aromatic rings. Carbons here, hydrogens on the outside. So lots of bonds, lots of energy being stored in all of those bonds. And these are just different ways that they can be arranged. Isomers is another term you might hear. They are molecules that have the same chemical formula, but their structure is different. So if we take a look at butane and isobutane, isobutane tells you it's an isomer. 4 carbons in butane, 4 carbons in isobutane. But look at the difference. So isobutane kind of makes a T shape, and butane has this linear shape. So they're just a different structure, but the same amount of atoms in each molecule. So when I count up the hydrogens, there's 10 there, and then there's 10 over here as well, but arranged differently. Geometric isomers are going to come into play, especially next week, where we have an arrangement of molecules around the carbons. And it's a little different. So this is cis and trans. Trans is like trans fats. And so the little functional group here is on the opposite side. So opposites, and cis means same. And so that's going to be on the same side. And then enantiomers are left and right oriented. So it's kind of like your left and your right hand. So you have a thumb and 4 fingers on your left hand, a thumb and 4 fingers on your right hand, but you can't superimpose them, right? If you put one on top of the other, it's just not going to completely fit on top of the other one. You're going to have thumb out to the side, right? Even if you flip it over, it's not the same because you're looking at your palm versus the top of your hand. So that's what an enantiomer is, a left or right, or like a mirror image. Here's a look at those cis and trans. So this molecule here, these are all carbons that are making up the center black structure. It's not a very good structure, but this is a carbon at each of these little bumps here, or these are hydrogen, sorry. The carbons are in the center. This is a trans fat, so nice and linear. This is a cis fat, nice and bent. Cis fats are better for us. Trans fats are not because they can compact. Notice if we put a bunch of these together, they're not going to compact. But this would be a good example of those things. And we're going to get more into that next week when we talk about biomolecules. But this is a long hydrocarbon chain, and I just wanted to show you what that looked like in a bigger setting. Okay. Functional groups. So functional groups are groups of atoms within a molecule that give specific properties to the molecule. Here's a hydroxyl group, so OH, methyl, CH3, carbonyl, carboxyl, amino, phosphate, sulfhydryl. Each of the 4 types of macromolecules, so carbs, proteins, nucleic acids, lipids, they all have their characteristic functional groups. So, for example, proteins, they have a lot of amino groups. DNA and nucleic acids have a lot of phosphate groups in them. And so you're going to have different ratios based on different macromolecules. Functional groups often interact with each other via hydrogen bonding. So we're not going to get rid of that term anytime soon. We're going to talk about hydrogen bonding throughout the whole semester. And it's it's just how important it is. Hydrogen bonds, again, stabilize biological molecules. So this is a molecule of DNA on this side. There's another molecule of DNA on that side, and they're being held together in the center here by hydrogen bonds. Typically, hydrogen bonds are showed by a dashed line so that you know that that's not within a molecule, it's between 2 molecules. So remember, hydrogen bonds are not in a molecule, they're between 2 separate molecules. And so this holds those 2 strands of DNA together and keeps it all organized within your cells. And they can be easily broken, separated. DNA can get copied, they can get put back together very easily, and so on. Okay, so you should be able to explain why carbon's important and why, or what functional groups are and why we talked about functional groups at all, really. And that is it. So hopefully that helps. If you need to go back and rewatch parts of the video, please do that. But I hope you have a great week, and I'll see you next week.